Thank you. Thank you very much, and I will try to please feel free to ask questions as I proceed, and I try to not have too many slides, so there should be plenty of time for that. I decided to talk about sort of these results about small changes in either the coefficient or the boundary conditions for PDEs, because I noticed that two of my collaborators have recently been talking about other work that I've been involved with on more directly inverse problems, namely Alba and Jingni. They were, I think, also recently talking in this forum. So this is sort of not directly an inverse problem, but I think it has had many applications and many implications for inverse problems. And so without further ado, let me go to the second slide. Let me just mention that the particular results concerning small change in boundary conditions is joint work with Eric Bonnetier and Charles Daponi. So, and let me also mention, I'll start with some background on internal perturbations. And this is, by the way, this is an area that's been active for quite a while, and many people have contributed. I will not try to give any references to work that has been done in this area. I'll rather try to give a very general background. I mean, if I try to mention names, it would be a very large list, and I would probably forget some, and so let me not get into that. Instead, I'll try to give sort of a general background. I will, however, just at the end, I'll mention the people that have been involved with me and that have collaborated with me on the things that I sort of talk about here. So the setup for the internal perturbations is that you have, let's say, it could be a wave equation, it could be a Helmholtz equation, it could, but let me take the simplest case of zero frequency, so the elliptic case, and you have a coefficient, I'll call it gamma epsilon, and it has a value. I mean, it could have, we could call it gamma 0 in omega minus little omega epsilon, but it's basically, it has some known value in a set, in the set, the omega is the total domain on which we're considering our PDE, and it's mostly, it has a value 1, or it could be anything, but just a fixed value, and could be a function, whatever. I make it as simple as possible. And but in the set omega epsilon, and of course I call it omega epsilon because we all think of epsilon as being small. And the thing about omega epsilon is that the Lebesgue measure of omega epsilon goes to 0 as epsilon goes to 0. So this is a small, volumetrically small set. And on that little small set, it has a different value, gamma, different from 1. So this is sort of, it's not a small amplitude perturbation, it's rather, because that would mean that gamma would be close to 1, it's rather a small volume perturbation, but the amplitude difference could be large. Actually, that's a very interesting case when the amplitude difference becomes large. And we have then the two problems. We have the perturbed problem here, that is divergence gamma epsilon grad u epsilon is equal to 0 in omega, with, let's say, just to make the solution non-trivial, with a non-trivial Neumann boundary condition on the boundary of omega. And by the way here, and it'll come up later, I assume that these are measurable sets that are bounded away from the boundary. So on the boundary, the coefficient is 1, which is why it's not a conormal derivative, but actually du dn is equal to psi. The unperturbed problem, of course, is, since I set gamma epsilon to be equal to 1 outside the little set omega epsilon. So when the little set omega epsilon has disappeared in the limit as epsilon goes to 0, the background potential, or the background problem, is Laplace u0 is equal to 0. And this should say, this is a misprint, it should say du0 dn is equal to psi. So I'll correct that on the slides before I send them. So that's the background problem. And now the game here, or the interest here, is to find out what is sort of an asymptotic of U epsilon when compared to U zero. So the basic result in this sort of these kind of expansions, and by the way, these kind of expansions, they have a long history also going back, and the name that's typically associated with them is Rayleigh. So the Rayleigh approximation, as opposed to the Born approximation, which is the small amplitude approximation. So this is the Rayleigh approximation, and there is a probability measure, and there is a tensor valued function m. By tensor valued, in this case, this would be an n by n symmetric definite tensor, and which does bear the name polarization. It's how the electric field is being polarized by the inhomogeneities. And the thing is that this polarization tensor and this probability measure, it only depends on the little sets omega epsilon and the changed conductivity gamma. It does not depend on the boundary load, the F that you put on. It doesn't depend on the capital omega. It's really intrinsic to the set of inhomogeneities. And actually, in a certain sense, for instance, if the little inhomogeneities were just a set of small balls, then that have, say, radius epsilon, then you could rescale these inhomogeneities, so to speak, and they would now be sort of represented by unit size inhomogeneities. And the polarization tensor M is directly calculable. You can calculate it from these rescaled inhomogeneities. So it basically contains information about the conductivity gamma and the geometry of the inhomogeneities. Whereas a probability measure will tell you something about where these inhomogeneities are located. And the formula, the representation formula, or the asymptotic formula, is the following that you could sort of prove, is that U epsilon minus U zero. So this is a perturbation in the voltage field, the perturbation in the voltage potential, and it's equal to this is the Lebesgue measure of the set. So when the measure here is small or zero, very close, goes to zero, this thing here will go away, and this little O of omega, this means smaller order than the Lebesgue measure, and so this one disappears also, which says that true enough, U epsilon in the limit converges to U zero. But there is a contribution at the level of the volume of the inhomogeneities. And this contribution, actually, the coefficient in front of that contribution is basically, it comes from this polarization field times the gradient of U. So this is how the gradient, the electric field, is being polarized. And here is the gradient of Y. This is you can think of it as a fundamental solution, but it's a fundamental solution with, say, in this case, since I'm looking at fixed Neumann boundary conditions, with Neumann conditions on the boundary. So this is why I call it N. It's sort of the Neumann fundamental solution. That means that this thing here that you have appearing here is a vector dotted with the gradient of this Neumann function. So this is what I would call, or people call, a dipole. And so what this first order perturbation is it's really the Lebesgue measure times an integral of some dipoles, a concentration of dipoles, and the measure that you measure here, you use, is sort of the probability measure that comes out from the location, and that's where the probability measures enter. So this measure would live on a very small set. For instance, if your sets are just small balls, it would be a point. It would be a set of point masses, of course, with a positive point masses and summing to 1. That's the probability part of it. And if, for instance, if your inhomogeneities were to center around a curve, this would be the measure of the curve. again, with the divided by the length of the curve with that particular, to make it a probability measure. And these things here would sort of tell you how the local geometry is, these inhomogeneities, how they look near the points geometrically, or how they look near the curve or the surface, whatever you're dealing with. I should mention, by the way, that we can give very precise bounds for the M's. They are very much related to the Hashim-Strickman bounds for effective media. They're basically the polarization tensor is sort of obtained in the small volume limit of the effective media theories, and you have bounds for them in terms of the conductivity gamma. And then these bounds will tell you what could all possible geometries give you for M's. This is how much I want to, but these kinds of formulas have been used in many applications, and I'll now make some remarks on that. Now, the first thing is, of course, that in this very general context, this only holds upon extraction of a subsequence. So it's a compactness result. It says that all possible limits of U epsilon minus U0 divided by the Lebesgue measure looks like such an integral here. And that's all possible limits. So you have to extract a subsequence first to get the particular limit here. If you were, for instance, saying, I know exactly, or these things don't move around the set omega, then you would get a specific limit. For instance, if you were to say that they are 100 small balls located at some fixed points and of some radius, then you would have a specific limit. But if you let these things move around, it's clear that you need to take a subsequence to get a representation formula like that. On the other hand, even though it is only a compactness result, and you would need to extract a subsequence to get to a particular formula, this has been, for instance, has been very useful in estimating the volume of the interior of the internal inhomogeneities from boundary data. And because then we know exactly what all of these constants here, these integrals, we can give bounds for them. As I said, there were bounds for M. You could say if the U0 comes from the linear function, then this is a constant, and you know what the Neumann function looked like. Then you can actually retrieve a lot of information about just the volume of the inhomogeneities. You want to locate the inhomogeneities, of course, you have to know that they are sitting, or you have to assume that they're sitting at fixed positions. So that's the first thing. It's really a compactness result, like in this theory of H convergence or homogenization convergence. The second result is the asymptotics is generally not uniform in gamma. So what does that mean? That means that if you have a conductivity inside the inhomogeneity that is gamma, then this expansion here, these things here are not, it's not uniformly valid. This is not uniform little o of omega epsilon, and this is not even uniformly bounded if gamma could go to infinity. For instance, think about having something that sits around a curve. If gamma in 2 dimensions, if gamma goes to infinity, then you will have a perfectly conducting curve. And if gamma goes to 0, you will have a perfectly insulating curve, a crack. And so U epsilon minus U0 wouldn't go to 0. I mean, you wouldn't have U0, the one without anything wouldn't be the limiting background field. So this all will depend on the fact that the uniformity of this would depend on the fact that the gamma is bounded away from 0 and away from infinity, except for special geometries. And that's actually something that has been very useful. So sometimes this is uniform, and it's sort of interesting to understand when this is uniform, and also to understand what is it that replaces an expansion like that if gamma is not uniformly bounded or bounded away from 0. And that's actually current work we are working on. I should say again, the asymptotics is in sort of not, I wouldn't call it the far field, but it could even be sort of the mid-distance field. It's away from omega epsilon. So this is not an up to the boundary of omega epsilon sort of asymptotic expansion. This is away from the set omega epsilon. And as I said before, also the set omega epsilon is supposed to be bounded away from the boundary. Now I'll give you some uses of these representation formulas. And they have been used, for instance, if you know that the set, if you have, as I said, you have a set of small sets that are located at some points Zj, say the centers are at Zj, then this representation formula has been used to reconstruct these locations. And actually, one of the things we have worked on, this was joint with Martin Brühl and Martin Hanke, was to use sort of a multiple signal classification scheme, a little bit like a sampling scheme, to actually find the locations. I don't want to go into details of that, but there's actually several papers on that by me and collaborators and other people. As I said, there's also the estimation of this volume, actually the Lebesgue measure of the set omega epsilon, based on one or more applied currents. And as I said, this formula here is asymptotic as omega epsilon goes to 0, but actually these bounds that we achieve actually are valid in a larger set, and actually that work has been extended by Graham Milton and collaborators to sets that are not necessarily small. The question of how do you, from boundary currents or boundary measurements, how do you infer what is the size of the set that sits inside in terms of its Lebesgue measure? And the things you can get from the asymptotic formula is, of course, only asymptotically valid in the small volume perturbation limit, sort of the dilute suspension limit or whatever you want to call it. Now, finally, and this comes to understanding when is this expansion uniformly valid? So when omega epsilon is a diametrically small set, for instance, a small ball or a rescale, a dilated set dilated by the factor epsilon, then so it means that what really goes to 0 is the diameter of the set, not just the volume of the set. So it's when it's like a small ball, as opposed to when it sits around a curve, where the curve can have a finite length, but the width of this little set around the curve goes to 0. That would still send the volume to 0, but it wouldn't make it diametrically small. And that's one of the things where you have problems with the uniformity of this expansion. But when omega epsilon is diametrically small, it's actually uniform. So this expansion here is uniform. This is something we proved with Hoi-Min Yin. And in that case, you would actually have the corollary of this is, since this is little o of omega epsilon, and this is omega epsilon, it says that u epsilon minus u0 in any norm you want on the boundary actually goes to 0 as omega epsilon's Lebesgue measure goes to 0, uniformly with respect to what you put inside. So it's just, I mean, a simple corollary of that is if you have a small ball in ND, it doesn't matter what conductivity you put inside. You can send the conductivity to infinity or you can send it to 0. The background is always U0. The U epsilon always converges to U0. It of course has something to do with the capacity of the limit set, and the limit set in this case is a point which has capacitance 0. So, and this will come up when we talk about perturbations of boundary conditions. And this has been used, the fact that this is uniform when omega epsilon is diametrically small, has been used to establish near investability estimates for approximate transformational cloaks. And this is, of course, an area that many people have worked on cloaks and approximate cloaks and so forth. And this is just saying that if you use this way, that's called transformational optics, where you blow up a small set to a unit-sized set, or you blow up a point to a unit-sized set in the limit, then these kinds of, this understanding of how small inhomogeneities behave, in particular independent of what sits inside, becomes important for estimating, or becomes one way of estimating what is the near invisibility of such approximate cloaks. And so this is actually, in this area, the people I collaborate on this particular aspect this also includes Bob Cohn and Mike Weinstein, and also Hoi Min. The collaborators here on the first part of it, really, it started with some work I did with Avner Friedman, then it continued with work with Sherry Moscow and with Yves Kaptebusk, and I'll not give any more references. What I want, so this is sort of the introduction to the internal perturbations. Maybe I should pause here for a moment and ask if there are any questions or comments, or at least give you a pause for my ranting. Okay, doesn't seem to be the case. I will then continue with what was really the topic of this, namely seeing, as I said before, the set didn't go to the boundary. Of course, there's been work on sending it to the boundary, but still an internal perturbation that where it approaches the boundary, and you could get similar kind of, you get the effect of the boundary felt. And there has been some work in the direction that I'm talking about now, that I want to talk about now, namely perturbations of boundary conditions. But in a sense, it's a natural continuation of this work, and it has many applications, in particular also to optimal design, that if I have time, I'll talk a little bit about. But of course, also knowing what these perturbations of changing the boundary conditions look like, knowing the signature of such changes in the data could, for instance, also be used to locate them. So it could be used, if you think of a changed boundary condition as measuring, say, corrosion on the boundary, it could be a tool in trying to find spots of corrosion on the surface from measurements that are far away from where the surface corrodes. I will not go into that much more than what I've just said. But I will say, what is a perturbation setting when we start doing perturbations of the boundary conditions? And I will take a particular simple example of perturbations of the boundary, namely when you perturb either a Dirichlet condition to a Neumann condition, or you perturb a Neumann condition to a Dirichlet condition. So the setting, the background setting, and I'll do this when these boundary conditions are homogeneous. So the setting here is that the background potential is one that satisfies Laplace u is equal to f for some f, and du dn is equal to 0 on the boundary. That is designated gamma n, that's the Neumann boundary, and u0 is equal to 0 on what I call gamma d, which is the Dirichlet boundary. So gamma n union gamma d, or the closure of gamma n union the closure of gamma d, makes up the full boundary of the set omega. I'll also assume that none of these are empty. So there's both a Dirichlet and a Neumann part, because otherwise I can't talk about both perturbing Dirichlet and Neumann conditions. So in the first perturbed one, when you take part of the Neumann condition and instead introduce a Dirichlet condition, what you do is you take the same inside equation, Laplace u epsilon is equal to f, but you now set du epsilon dn is equal to 0 on gamma on the Neumann boundary part minus this little set. And then you instead introduce u epsilon is equal to 0 on gamma d, the full Dirichlet boundary from before, union with this little set. So you basically introduced a Dirichlet boundary condition as a homogeneous Dirichlet condition as opposed to a homogeneous Neumann condition. So for instance, in structural mechanics, this would mean that if you were to do this for the equations of elasticity, you would, instead of having a free part of the boundary, you would have a rigid support, you would clamp it. And of course, that's what people in optimal design are often interested in finding out. Where should I put my clamp parts of the boundary? Where should I make it rigid? And where should I let it be free? And understanding how small changes this would make it sort of possible to find out nucleate, where should I nucleate a change in boundary condition? And then once you have nucleated it, you would probably you would have some kind of flow algorithm for growing it. But the first part is, where would it make sense to build these rigid parts? And that could come from understanding what is the signature in your, for instance, if your optimization is a compliance-based optimization, what is the impact on the compliance of introducing an extra Dirichlet condition as opposed to a Neumann condition? Similar, what would be the effect on the compliance of introducing an extra freeing up part of the boundary as opposed to having it rigid or clamped? So that would be one application of this. And I'll actually, if I have time, I'll do the compliance calculation later on. So as I said, in the first case, gamma omega epsilon is a part of the Neumann set over here. And in the last case, it's a part of the Dirichlet set. The goal is to find an asymptotic expression for u epsilon minus u0. So much like before, what does to first order, what does a change look like? But here the question is also to understand, what is it that has to be small in order for u epsilon to converge to u0? So what does it mean that you have a small perturbation in boundary condition? Because it's not that the boundary condition that you have a coefficient that changes ever so slightly. You are changing the boundary condition dramatically, but on a small set. And the question is, what is the smallness of the set that makes actually u0 be the background potential? And so that's what I will first give you here in terms of the general representation formula. So omega epsilon, again, I'll assume here that it consists of a finite number of connected open Lipschitz subdomains. So you have on the boundary, you will have sort of a finite number, and they will have a Lipschitz boundary. There will be subdomains there, so each of them will be connected. And the closures of each of these little things do not intersect, so they are separated apart. So that's what will be the assumption about the set omega epsilon on which you are changing boundary conditions. I will assume that omega epsilon lies either strictly inside gamma n or strictly inside gamma d. So when you're changing boundary conditions from Neumann to Dirichlet, omega epsilon lies strictly inside gamma n. And if you're changing from Dirichlet to Neumann, omega epsilon lies strictly inside of D. And this is actually, this is sort of the thing I had here, this little thing that I had drawn over here. I have a sort of my rendition of a 3D domain, and this is gamma D. This is a Dirichlet boundary part. This is a Neumann boundary part. And I'm assuming that these little sets on which I now impose Dirichlet boundary conditions as opposed to Neumann boundary conditions, they sit separated away from the Dirichlet part by this set sigma that has some kind of minimal distance. So that's sort of the pictorial that illustrates this. Now the representation formula, if we take this, if we replace Neumann boundary conditions with Dirichlet boundary conditions in such a small set, is u epsilon is equal to u0. So just, it looks sort of like before, u epsilon is equal to u0 minus, and now the Lebesgue measure gets replaced what I call, and this is what actually people will call this capacity of omega epsilon, but I'll call it the Dirichlet capacity of omega epsilon. And then there is a coefficient here. Now, in this case here, it doesn't involve actually any geometry. There's no coefficient change inside. It was a boundary condition change, so there's no polarization tensor. But there is still the same Neumann function. Well, in this case, it's a Neumann-Dirichlet function, but it's a fundamental solution that corresponds to the background problem. And then there is a u0, which is a field in the unperturbed state. And so this is a coefficient that is in front of the change that gets multiplied by the capacity, the Dirichlet capacity of the set omega epsilon. And then it's plus little o of the Dirichlet capacity. So this is the leading order term. It says u epsilon minus u0 is equal to this term. And this is for x that is compactly contained in omega, right? The change sits on the boundary, so you have it here away from the boundary. You could actually go out to the boundary, so I didn't want to get technical here, but you can go out to the boundary, but you can't go near the set omega epsilon. So this is again expansion away from the set omega epsilon. And the fundamental—
I have a question.
Yes.
What is the capacity?
Well, that I'll come to that on next slide. What is the capacity?
Okay.
So I'll give you that, how it's defined. And then I'll also actually later on spend time defining what is a Neumann capacity, because there is a different capacity when you change from Dirichlet to Neumann conditions. And that's at least, that requires also a sort of a new definition. So the fundamental solution here is, of course, this is built on the, as I said, the assumption is that both gamma n and gamma d are different from zero. So there's no equilibration. There's nothing with that this has to be equal to a constant that sort of that matches the delta x. You have both a Dirichlet and a Neumann part. So this is the natural. This is the natural Neumann, the way of defining a Neumann function for the background problem. Okay, but now to the question of how is a capacitor defined? So here is what the capacity is. So the capacity is defined as the following. It's the minimum, and this thing here is, you can say this is the H1 norm. So it's a minimum of H1 norm. So all of omega, this set this omega where we're looking at this omega here is it sits inside RD. So it's a d-dimensional domain. So we're looking at this in d dimensions. And so now what you do is you simply take the integral, you take the H1 norm, or the H1 norm squared actually, of functions that are in H1 and which happen to be equal to 1 on this set. And then you minimize that. So it's simply defined as the function, as a minimum of all H1 norms, subject to the restriction that you want V to be equal to 1 on omega epsilon. So that defines, that's a standard definition of capacity. I mean, there are people who, I mean, have this is the sort of the free space capacity, because it completely makes the capacity of a set be independent of that it sits on the boundary of omega, right? I mean, you don't want the capacity of the set, or like you don't want the Lebesgue measure of the set to be dependent on that it sits on the, you want to, the Lebesgue measure, of course, depends on the particular dimension that you are talking about, but you don't want it to be dependent on that it sits inside a particular set omega. Here you are defining this completely independent of the set omega. But there is something that you could say, what if I want to relate this to a boundary value problem on omega, namely take the following boundary value problem on omega, take the Laplacian to be equal to 0. In that case, you don't need a lower order term, just take the Laplacian to be equal to 0. The fact that you need a lower order term is otherwise, if you minimize just the gradient squared, subject to, then the solution would not be in H1. So that's why I add this extra term. But if I'm on the bounded domain omega, then I could define the function that solves Laplacian chi epsilon is equal to 0 with the Neumann boundary condition on gamma n minus this little set, and then the Dirichlet boundary condition on gamma d, and then 1 on omega epsilon. So this would be a way of sort of defining a function that only lives on omega, and that sort of does what these functions up here are supposed to do, namely takes a value 1 on the set omega epsilon that now sits on the boundary of omega. And you could then say, well, what if I take the energy, the Dirichlet energy of this function, the gradient chi epsilon squared, then you can actually it's not too hard to prove that this Dirichlet energy is equivalent to this capacity, which was independent of your domain, except for the fact that these constants little c and capital C get to depend on your domain omega. So they become dependent, I should call them little c omega and capital C omega, because this function chi epsilon depends on omega, and that is reflected in the constant. The equivalence constants are dependent on omega. And there's another thing that I will note. Not only is this Dirichlet energy equivalent to the capacity, but you also have that if you look at the L2 part, and that's why I said it doesn't matter whether you have a 0th order term here, the L2 integral of this function is actually smaller little o of the capacity because it's a capacity to the power 3/2. And that I will use as well. Okay. So does that sort of clear up what I meant by capacity, or what is meant by capacity?
Do you have an explicit example, like which kind of omega epsilon have, what is the capacity of it?
I will give that at the end. So yes, I will calculate specific examples at the end with what the capacity is.
Yeah, thank you.
Okay. So now we just calculate the following. So I want to give you a calculation of this thing here. So you have this function, and this becomes a little bit technical, so I may skip over it. But let me not skip over this first part here. So now if you take this function chi epsilon that was defined here, so it's the one that solves the Laplacian with 0 boundary conditions on gamma d and this little set, and the Neumann boundary condition 0 on gamma n minus little set. Let's now calculate just the integral on the boundary of the normal derivative of this chi epsilon times any smooth function. So if you calculate this with any smooth function. Now what is this equal to? Of course, this is equal, you can just do integration by parts. This is the gradient dotted with n times chi epsilon phi. So if you just take and say that's equal to the divergence of this, then you get the Laplacian of chi epsilon, which vanishes, and the other part you get is the gradient of chi epsilon dotted with the gradient of chi epsilon times phi. So this is just integration by parts, noting that the chi epsilon satisfies the Laplace equation inside Laplace chi epsilon is equal to 0. I've here divided by 1 over the capacity, I've divided by the capacity, I've divided by the capacity. Now, when I calculate this gradient here, well, you use the product rule, this becomes a gradient of chi epsilon times phi plus chi epsilon times the gradient of phi. And I want to make the point that the only thing that the one that's of leading order is when I take the gradient of chi epsilon times dotted with the gradient of chi epsilon times phi, which is what comes in here. This is what is of leading order, because the other thing, when I don't put a gradient of chi epsilon, then I have sort of the gradient of chi epsilon, and I have chi epsilon squared. And then I use just what I had on the other side. I use the fact that I use Cauchy-Schwarz, and the L2 norm of this is the capacity of omega epsilon, the square root of that, and the L2 norm of chi epsilon is the capacity to the power 3/4. Well, if I add 3/4, and 1/2, I get 5/4, since I'm dividing by the capacity that takes care of 1, and so, but I'm still left with a capacity to the 1/4. So this is, if I assume that this is a C1 function, smooth function, doesn't have to be C1, or let's say it's a C1 function. I took the gradient of phi, so it's a C1 function. So then I have something here that is little o of 1. So it means that in the limit, this will disappear when capacity of omega epsilon goes to 0, which says altogether that if you look at this function 1 over the capacity of omega epsilon times this product here on the boundary, it is actually, so this thing here would be, it's bounded if you look at it as a distribution or as a linear functional on C1 functions. This thing here actually goes away. It's bounded by C1, but it also goes away. And this thing here would actually say that it is bounded, because on the previous slide, I proved that this thing here is equivalent to the capacity. So this thing here divided into this itself is bounded. So this actually says that this thing here is bounded in the dual of C1, which of course, since C1 is a norm vector space, it says, or it's a Barnack space, it says that it converges weak star when you integrate it against the C1 function. And actually it says not only it converges to some mu, and this is actually, this will be the Radon measure that appears. Remember here, I had a Radon measure that appears here, and this is exactly the definition of the Radon measure that will appear here in the representation formula, this mu, which was what replaced the probability measure from before. Now, this also, since this thing here disappears when omega or epsilon, when the capacity goes to 0, this thing here is actually bounded by the Z0 norm. So the limiting thing, mu phi, will actually be bounded by the Z0 norm. So it's in the dual of continuous functions on the boundary, which means it's and it's a positive, so it's a positive Radon measure. And mu phi, I'll therefore write as integral over the boundary of phi d mu, this positive Radon measure. And so this is the measure that appears in your representation formula. It's the weak star limit of this. But this is, of course, where the extraction of a subsequence comes in, because what I used here is I used the Banach-Aloglu theorem that sort of says what happens with the bounded, with the unit ball in the dual of C1, and the thing is it's weak star compact. But that means that I can extract a subsequence, and that's where this comes in, that it's a compactness result. Again, as before, if you know that these inhomogeneities or these changes in boundary conditions are located at a particular point, they don't go around the boundary, they don't walk randomly around the boundary, then you get specific limits. But in general, you would have to extract a subsequence to get these specific limits. Okay, any questions at this point? And the support of this Radon measure lies inside any compact set that contains these omega epsilon. Now, I will actually, I'll try to, these things here that I have here is, I have that the H1 norm of the, I introduced the discrepancy between U epsilon and U0. And so you look at this in H1 and you look at this in L2. What is actually, these things are not, R epsilon is not that far away from the chi epsilon, because what was it the chi epsilon had? The chi epsilon had 0 Neumann boundary condition on this set gamma epsilon minus omega epsilon. It had 0 boundary condition on gamma d, and then it had a 1 boundary condition on omega epsilon. What does this function u epsilon minus u0 have? Well, where u0 is 0, so the 0 boundary condition, the set gamma d is also a 0 set for u epsilon. So this R epsilon vanishes on gamma d. It on this little set omega epsilon, what happens there? Well, u epsilon vanishes on omega epsilon. That's how you introduced it. So it's equal to minus u0. And on the part where the boundary conditions were Neumann, except for on the set omega epsilon, this thing here had 0 boundary conditions, and this thing here had 0 boundary condition. So the only difference in this function R epsilon and the function chi epsilon that I have over here is that R epsilon satisfies this equation, except for R epsilon is equal to minus u0 on this set omega epsilon. It's not 1, it's minus u0, but since this set is sort of shrinking, in the limit, you could understand why the formula that would come in would involve u0 and then somehow the capacity of the set, which comes out from calculating the energy of chi epsilon. And so that's, therefore, it's not surprising that the R epsilon will satisfy the same bounds as chi epsilon. The H1 norm would be equivalent to the capacity, the square root of the capacity, and the L2 norm will be equivalent to will be bounded by 3/4 of the capacity. And of course, now the constant would depend on U0, but it has this bound here that the H1 norm is bounded by a constant times the square root of the capacity, and the L2 norm would be bounded by a constant times the 3/4, the capacity to the power 3/4. Now, if you then calculate, so what I'm just doing here, this is what I did before. In this case here, the only set that you act when you're integrating on the boundary, since this thing here, if you take a C that vanishes on the Dirichlet boundary, this thing here vanishes on the Neumann boundary minus omega epsilon. So this is all an integral on the little set omega epsilon, which is why you can introduce the you can introduce a function chi epsilon, which is equal to 1 on this set. Then you integrate by parts, you get the gradient of R epsilon dotted with the gradient of chi epsilon psi. Then you do the thing that I did before. You can drop the thing when you have chi epsilon times a gradient of R epsilon, because that becomes a question of the H1 norm and an L2 norm. And so the leading part of this volume integral is really when the gradient gets passed on to chi epsilon. The psi then comes out as a multiplier here. Everything else is of the order of the capacity to 5/4. You do that once more, and you get an R epsilon, and then you get the d chi epsilon dn psi. So basically this goes one way, and then this goes back onto the boundary. Now you can, again, this is only an integral on the little set omega, so you can introduce a function chi epsilon. And so now on this little set omega epsilon, R epsilon is equal to minus U0. And so altogether you get this formula here. But see, this thing here was what we found the weak star limit of before in C1. And so now we just have to pick a test function that is, again, a C1 test function, and we can use the fact that this thing here converges weak star to something, and this thing here disappears when we divide by the capacity to the power 1. And so what I set in here is I introduce C is equal to the Neumann function evaluated at a particular point, but with the second variable as being the variable. So now what you do here is you take this R epsilon, replace C by N of basically of the second argument here. So that's where you get this thing here integrated on the boundary. You put that in over here. So you have U0, then you have this thing here, and you have now N here. So that is basically what I have here. And then I have the order of capacity to the 5/4. Now I have that I can then use, when I divide by the capacity here, I get that this thing here, so I take this previous, I divide by the capacity, and then I divide by this thing here by the capacity, but this is what we before had converged weak star to something. And since this thing here is a smooth function when y is near omega epsilon, x is away. I said you cannot approach the set omega epsilon. This thing here is a smooth function because I assumed the sets did not approach where U0 had a change in boundary condition from Dirichlet to Neumann. So this is all a C1 function. And so this function here is one that you can use for the weak star convergence. And this thing here was exactly what I had over here. I had the d chi epsilon dn chi epsilon 1 over the capacity, weak star converges to mu. And so that's where I introduce the Radon measure mu now. So I have that this thing here converges to this particular expression here. Now we just have to say what is U epsilon minus U0. Well, U epsilon minus U0 is R epsilon. Well, that's equal to, I introduce the fact that this is minus a delta function. So that's just using the fact that this is a fundamental solution. Then you integrate by parts. You have lots of zeros on the boundary because the gradient of the normal derivative vanishes on gamma n minus omega. And this thing here the Neumann derivative vanishes, the R epsilon vanishes on gamma D, actually union with the set omega epsilon, and the normal derivative vanishes on all the set gamma epsilon, gamma n, so you can integrate by parts here. Then you integrate once more by parts, you have enough boundary conditions. So this actually says that the U epsilon minus U0 is equal to this thing here, which is exactly what you're calculating the limit of here, modulo dividing by the capacity. So now if I divide by the capacity here, the limit of that becomes equal to the right-hand side, which is what I have here. The limit of the capacity, U epsilon minus U0, becomes equal to this expression here. You remodel that, multiply through by the capacitance, put it on the other side, and you get that U epsilon is equal to the background potential minus the capacity times this integral here with the monopole, the U0, and then you have plus a little o of the capacity at D. And this integral here really only lives near where you've changed the boundary conditions, because the support of this measure sits inside any compact set that surrounds these little sets that you're changing it on. I will not do this compliance calculation. I'll leave that, the slides will be up there, but I'll just mention what is it that happens when you do Neumann boundary conditions. Well, when you do Neumann boundary conditions, so now you are introducing something that sits inside gamma D, you're introducing a Neumann boundary condition, you get a similar expression. Now it depends on the Neumann boundary condition of U0 on the set, and depends on the normal derivative of the Neumann function. And there is again a Radon measure showing up here. The thing is, what is a little E of epsilon? What is the capacitive replaced by in this case? Because it's a Neumann capacity. And I will just do that. And what I do is we take a function which is sort of, I said that omega epsilon had finitely many connected components. Make a choice of either plus or minus one on each connected component. And then you solve the following problem in all of RD, namely minus Laplacian plus ZK is equal to 0 in outside of this little set. And on the little set, you have that the normal derivative, you pick a direction, is equal to either plus or minus one on each connected component. Then you do this for all choices of plus minus ones, all directional choices. And you maximize, you take the maximum of this norm here, the sort of like the H1 norm, and that'll be the Neumann capacity. And that's the thing that enters in here it's independent of your domain omega, and it plays a role of the Dirichlet capacity when you're changing Neumann to, when you're changing a Dirichlet condition to a Neumann condition. I must say, I have not seen this definition of Neumann capacity before, but I wouldn't be surprised if it's found somewhere. Again, you can show that it's equivalent up to constants that are depending on the domain to a function which solves the Laplacian, where you have exactly done what we are talking about. You've taken the Dirichlet boundary condition and replaced it by a Neumann condition of 1. And that's exactly what you did for the Dirichlet capacity also. This, and then you calculate the Dirichlet energy of that, and that's equivalent to this new notion of Neumann capacity, or of Neumann capacity, except for the fact that so you could say, why don't I use this? Because then it wouldn't be intrinsic to the set omega epsilon. It would also involve the domain omega, because these constants are dependent. So I don't have much time left. I don't want to go through the, I don't want to go through the calculation. It's the weak star limit of this function psi zeta epsilon times zeta epsilon divided by this Neumann capacity that you can prove is bounded, and the weak star limit of this gives you the Radon measure. Again, you can do a calculation with compliances. Now, I was asked what are concrete examples. So if you take a domain omega and you take what I'll call a surfacic ball. So a surfacic ball will take a point that sits on the boundary and take omega epsilon to be the intersection between that ball and the boundary. So it's sort of the intersection of a ball in the ambient domain with the boundary. And so it's a surfacic ball of radius epsilon is what I will call it. And then the capacity of this in 2D, so when the ambient space is R2, will be capital O of 1 over the logarithm of epsilon. So it depends, basically it's equivalent to 1 over log epsilon, where epsilon is a radius. When D is equal to 3, so a surfacic ball on this two-dimensional manifold will have a capacity equivalent to epsilon, the radius of it. And if you look at the Neumann capacity of this set in 2 and 3D, it would be epsilon to the D. And I could give you all kinds of, I don't have much time, so I won't do that here, but there are very good sort of intuitive reasons why these should be the results, but this is also fairly easy to prove. In this case, the mu and nu will be point masses. They center at the point U0. And so what you get for the expansion for inserting of a homogeneous Dirichlet boundary condition into the Neumann set. So this is when you replace a Neumann boundary condition by a Dirichlet condition, you get that U epsilon is equal to U0. And as I said, this is in 2D, so the capacitance is equivalent to 1 over log epsilon. And the constant here is pi. This is the Radon measure is pi times the point mass. And U0, Y0, N of X0, Y0, and then plus a little O of epsilon. So that's one. And in 3D, it would be equivalent. It's the capacity is equivalent to epsilon, and the constant in this case that sits on the Radon measure is 4. So it becomes 4 epsilon U0 evaluated at this point where you, in the neighborhood of which you change the boundary condition, and then the Neumann function. For the homogeneous Neumann boundary conditions, when you introduce that on a set in gamma D, in the Dirichlet set, then you get the background field, and then you get AD times epsilon to the D. As I said, the capacitance was the capacity was equivalent to epsilon D. Then there was this normal derivative of your background, and then the normal derivative of the Neumann function plus little o of the capacity. And this AD is equal to pi over 2 in 2 dimension, and it's equal to 4 over 3 in 4/3 in 3 dimensions. And this is where I'll stop. Thank you for your attention. If there are any questions, I'll be happy. You can look up my Google Scholar page. You can send me an email. I'll be happy to discuss these things with you. Thank you.
Thank you very much. Thank you very much, Michael, for the very, very nice talk. Thank you very much. Are there any questions or comments?
Yeah, so this eventually this mu, this Radon measure is supported on this Y0, and is there an intuitive way of thinking of where this Y0 is? Is it?
Well, I said you started out with a set omega.
I see.
That is centered at Y0, right? So that's why I'm saying it's not wandering around. It's actually centered. It's a basic ball with a center of Y0, and that's why it's exactly it's a delta mass at Y0. And of course, the question here, and that's actually not trivial to calculate. It took us quite a while to calculate what these. We all do this by boundary integral formulations and actually hypersingular integrals. And to find these particular values of the constants, the pi in 2 dimension is odd, but the -4 in 3 dimension and the 4/3, it's not trivial in 3 dimension to find these constants.
Thank you.
Thank you very much. Are there any other questions or comments, please?
By the way, I should, let me just mention also to make a connection with other work. There has been a study, the fact that you take a little set and you introduce a Dirichlet boundary condition. There is a sort of they're typically they're referred to as escape problems, because you can think of it as sort of putting and in this case, since it's narrow, the name, if you look up in the literature, there's something called the narrow escape problem. And the narrow escape problem is exactly, you have a place where you normally have no flow, and you suddenly permit a flow by saying a zero boundary condition. And now it's like you've attached a little tube and your fluid is perfectly happy to go out there. And it's been used for modeling actually in math biology, these narrow escape problems. And this sort of tells you what is the effect of setting out such a tube, such a narrow escape. What is asymptotically the effect of it? And it could tell you, for instance, in a biological application, where should I put my quote unquote, the tubes of the narrow escape problem?
Thank you very much. Thank you very much. Are there any other questions or comments, please? Okay, if not, thank you very much.
Oh, sorry. I have a question. I just wasn't sure if. Sorry, just I'm asking for a quick response. First, thank you.
You will get a quick response, I promise you.
Okay, thank you for your talk. I have a basic undergraduate question. If no one else has a better question, my question is, at a high level, from an applications perspective, given a problem with Dirichlet boundary condition, why or when would you want to change to or introduce Neumann boundary condition?
Well, I mean, you could think of it in two ways. You could think of it, let's say that you have a boundary where you think there are Dirichlet boundary conditions. You can't see the boundary, but you think there are Dirichlet boundary conditions. On the other hand, maybe there's corrosion appearing, and corrosion is typically associated maybe not with a Neumann boundary condition, but some kind of Aubin boundary condition where you have some relation between the normal derivative and the potential value at that point. And so it could be interesting, for instance, to say, could I find these spots where the boundary condition has been changed? You're not introducing a boundary change, but the system has introduced a boundary change. You thought there was Dirichlet, but actually it's rusting there. There is a Neumann boundary condition or Aubin boundary condition. And now can you find those kind of spots where it has rusted based on information from the other part of the boundary? Let's say from the boundary, let's say you're looking at a pipe from the other side of the pipe, where you can measure, because you can't measure maybe inside or that backside where you think there is rust. And now you can measure the data there, and then you could say, okay, this is what a change should look like. Does this change that I'm observing by my measurements, where does that correspond to a rusting spot or a changed boundary condition? This is all assuming that you have a structure where you can calculate U0, so that you do some measurements and you can subtract U0, and that sort of becomes your perturbation measurements. You never, when you do inverse problems, you never want to measure, take the full data that you get. You want to somehow say, well, this represents a change on something else, and I can calculate the field of that something else. And then what I really want to measure is the change. And that change should relate to, in this case, the change in boundary condition. Another thing would be, as I said, if you were a mechanical engineer and you wanted to find out where you should either support your object or you should let it have a free boundary, you would want to find out what is the effect of clamping the boundary at a particular spot. And again, these are things that tells you what is the incremental change that comes about from changing, say, from a clamp to a free boundary or from a free to a clamp boundary.
Thank you, Chris. Great answer.
Thank you very much. Thank you very much. Are there any other questions or comments, please? Okay, if not, thank you very much, Michael, for the very, very nice talk. Thank you very much. Thank you very much, everyone, for coming. Thank you very much.
And I'm sorry for not directly talking about inverse problems, but
it's great. It's great. Thank you very much.
Okay.
Thank you. Thank you.
And thank you for having me.